Again, I'd like to welcome everybody to today's webinar, Continuous Delivery to Amazon ECS. Our presenter for today is Jeremy Cohen. Jeremy is currently a solutions architect at AWS, where he specializes in container and directory services. With over 20 years of industry experience, Jeremy comes to AWS after having worked for VMware, Microsoft, and IBM. Today with us, we also have Drew Dennis and Daniele Stropa. They're going to be our webinar moderators today, who will be engaging with you and answer your questions through the Q&A panel. Jeremy, at this time I'd like to welcome you, and the floor is yours.
Great, thanks, Jerry. Appreciate the introduction. Welcome to this AWS webinar on continuous delivery to the Amazon EC2 container service. My name is Jeremy Cohen, and as Jerry said, I'm a solutions architect at AWS. For the next hour or so, we're going to be talking about the virtues of containers, the different stages of the software development lifecycle, and how you can automatically build, test, and deploy your containers onto ECS. So let's start by looking at continuous delivery. Continuous delivery is a software development practice where code changes are automatically built, tested, and prepared for a release to production. It expands upon continuous integration by deploying all code changes to a testing environment after the build stage. When continuous delivery is implemented properly, developers will always have a deployable build artifact that's undergone a battery of tests. With continuous delivery, every code change is built and then pushed to a test environment. There could be multiple parallel test stages before a production deployment occurs, after which the developer assesses the code's readiness for production and decides whether the update ought to be pushed. Now, this is slightly different from continuous deployment, where the push to production happens automatically without explicit approval from the developer. Continuous delivery lets developers automate testing beyond just unit tests, so they can verify application updates across multiple dimensions before deploying them to a production environment. These tests may include UI testing, load testing, integration testing, API reliability testing, and so forth. All of these tests help developers discover and remediate issues in the development cycle. With the cloud, it's easy and cost-effective to automate the creation and replication of multiple environments for testing. This is oftentimes challenging or cost-prohibitive to do so on premises. Now, a lot of you are probably familiar with the virtues of using containers, but here's a quick summary of why they've become so popular. Containers are similar to server virtualization like EC2. However, instead of partitioning the machine into multiple VMs, containers isolate the processes running on a single operating system. Containers are portable too, in that they can run on different operating systems without modification. And because the container image is consistent and immutable across environments, you can move containers from your desktop to production with relative ease. Containers also start quickly because the operating system is already running. However, simply saying containers are fast are doing them a disservice. They also accelerate the development process, as we'll soon see. And finally, containers are efficient in that you could specifically allocate the resources necessary to run your processes. And since containers share the same OS kernel and libraries, containers use less resources than running the same process on different virtual machines. So all that's great, but how do containers relate to continuous delivery? Well, continuous delivery is all about reducing risk and delivering value faster by releasing small, discrete updates more frequently. That requires that your software be deployment ready throughout the development lifecycle. It requires fast and automated feedback on the production readiness of your software whenever you make changes to your code. And it requires an ability to perform push-button deployments of any version of the software to any environment. Containers help you reduce the risk of introducing errors because they provide a consistent and predictable environment throughout the different stages of the development lifecycle. And given their lightweight, small in size, and start quickly, they could increase your speed and agility. So this is what a typical deployment workflow looks like. First, developers write some code on their machine and push those changes to a code repository like Git or code commit. Push triggers a build, and artifacts are built. Tests are then run, and assuming all the tests pass, a new version of the software is deployed to production. Now, orchestration is the key to this process. It controls how the code or your build moves from one stage to the next. We'll now dive deep into each stage and explore where and how containers can be used. All right, so the first step in the development process is the source code. You typically start the development process on your local machine. You write some code, test it locally, make some changes until you're satisfied with it. When you're finally done, you push it to a code repository. This can be a distributed system which allows multiple developers on the same team to work on the same project together, like GitHub. So what tools can we use for this? What can we use to define our containers? When we talk about containers, we're often referring to Docker containers. Docker is available for a lot of modern Linux distributions as well as Mac and Windows through the Docker Toolbox, and as of a few months ago, a Docker beta for OS X and Windows. With Docker, we can define the environment an application will be executed in and any additional dependencies in what's known as a Dockerfile. In this example, we start from a Ruby base image and install some additional packages using the OS package manager apt-get. Then we specify our application dependencies using a gem file, and finally we copy our source code. This Docker file can now be used to build a Docker image that we can use to run our containers, and we can use the same image throughout the different lifecycle stages. A lot of people are attracted to Docker because of its growing tools ecosystem. One of these tools is Docker-Compose, which allows you to run complex applications that are comprised of multiple containers. With Docker-Compose, you first need to create Docker files for each of your application components. Next, capture how these components interact with each other in a Docker-Compose YAML file. Once you have a YAML file, you can use the Docker-Compose up command to deploy and run all the containers that comprise your app. So here we have an example of a Docker-Compose YAML file with two services, a proxy service and a web service. The proxy service is built from the Docker file in the proxy directory. It maps port 80 on the container to port 80 on the host, and it's linked to the web service. This will allow us to refer to the web service container as web from the proxy service container. The web container is also built from Dockerfile located in the web directory. Since it's a Rails app, we specify the command we want to be executed. It also exposes port 3000 to any linked services that are not on the host machine. So now that we made some changes to our code, let's have a look at the setup we have to build new artifacts. At this stage, containers will be used in two ways. The first is to provide an execution environment for the build jobs and as an output of the build process itself. In a moment, we'll see how we can run our builds on an ECS cluster and how to produce container images that we can use throughout the rest of the development lifecycle. As we start building more apps, the time it takes to execute them will become long enough that we'll want to distribute their execution across multiple machines. The EC2 container service, or ECS, can help to distribute build jobs across a cluster. For example, if you're using Jenkins with the CloudBees Jenkins ECS plugin, you're able to run build jobs on an Amazon ECS cluster. This plugin will connect your ECS cluster, create new task definitions for Jenkins slaves, execute your job, and tear everything down when the job completes. Doing things in parallel like this further accelerates the development lifecycle. Now, containers are also the output of the build stage. The latest code changes are packaged in a container image and pushed to a repository. For instance, when you use the CloudBees Docker build and publish plugin for Jenkins, Jenkins automatically builds container images and pushes them to a Docker registry. You simply have to specify the repository name you want to push the image to, specify a tag for it. In this example, we're tagging it using the Jenkins build number, and then the URL of the registry you want to use. In this example, we happen to be using the Amazon EC2 Container Registry, or ECR. ECR is a fully managed Docker container registry that makes it easy to store, manage, and deploy your Docker container images. And since Amazon ECR is integrated with the Amazon EC2 container service, it further simplifies your development to production workflow. By using ECR, you eliminate the need to operate your own container repositories or worry about scaling the underlying infrastructure for those. Additionally, ECR is backed by S3, which is a highly durable and scalable storage platform. All this allows you to reliably and consistently deploy containers for your applications using familiar commands like docker push and pull. And finally, ECR's integration with AWS's Identity and Access Management Service gives you the ability to apply fine-grained access controls to each of your repositories and audit access of those repositories. So once our build is complete, now we're ready to run some tests. Now you can run tests inside of or against a Docker container. When you run tests inside of a container, you can launch the container using Docker commands and parameters as seen here. This builds on the Dockerfile for the Rails application that I showed you earlier in the deck, only here we're adding rake test. Rails is a good language for testing because it has its own test framework that produces skeleton test code as you write your app. It can also simulate browser requests without a browser. Now, if you have a lot of unit tests that are going to take a long time to execute, you may want to run them outside of the container and limit the number of integration tests you do against the Docker image. One way to do this is by running your containers in detached mode with an exposed port. Once your app's running, you can use an automated testing solution like a Pika or Blaze Meter or Ghost Inspector to run browser and other black box tests against your app. So now that we've covered the build and test stages, all that's left to do is deploy our new version onto our production environment. On AWS, there are a couple of ways to deploy and run Docker containers. The first way is to use the EC2 container service, or ECS. ECS is a scalable container management service. Doesn't matter if you want to run a dozen or thousands of containers, ECS will seamlessly scale to provide consistent performance. Additionally, ECS includes a set of schedulers for running tasks and services that you can use to place containers on instances within the cluster. It also exposes the cluster state through a set of APIs so you can create your own custom schedulers or use third-party schedulers like Mesos. ECS is also highly integrated with other AWS services like CloudWatch, IAM, and autoscaling. Now, for those of you who are new to ECS, here are some basic concepts you ought to know. A cluster is simply a collection of compute resources. Container instances are EC2 instances with the ECS agent installed on them. And a task definition defines the configuration of your containers. It includes the system resources like CPU and RAM, network and storage settings, and container images along with their parameters. If you're familiar with Docker, it's similar to the output that you get when you run Docker inspect. Now, ECS has had several updates and feature enhancements over the last few months that make ECS an even better platform for running your containers and microservices. The first is task roles. Task roles allow you to assign an IAM role to a specific task. By assigning an IAM role to tasks instead of instances, you're now able to run different services on the same ECS cluster without fear of granting elevated privileges to other services running on the cluster. We also introduced an application load balancer that works in conjunction with ECS to discover the host port that your containers are dynamically assigned by Docker. Instead of using a fixed port, you can now use dynamic ports and let the ECS scheduler automatically add your tasks to the application load balancer using this randomly chosen port. Previously, you had to define a fixed port for your container in order to use ELB to route traffic to your application. This prevented multiple copies of the same task from running on the same host. There was also a one-to-one mapping between ECS services and ELBs, or elastic load balancers, which increase the cost and complexity of running microservices applications on ECS. The ALB, or Application Load Balancer, can be shared by multiple services using path-based routing too. Each service can define its own URI, and that URI routes traffic to that service. For example, you can have two services running on the same cluster where one service is responding to requests on, say, acme.com, and another service is responding to requests on acme.com/img for images. Another recent enhancement is auto-scaling policies for services. Like auto-scaling for EC2 instances, which you can use to dynamically scale the size of your ECS cluster, auto-scaling for ECS services allow you to use a CloudWatch metric to dynamically scale the tasks in your service. And finally, there's now support for all the different networking modes that Docker supports: bridge, host, and none. Together, these allow you to have greater control over the networks that your applications run on. Another way to deploy Docker containers within a pipeline is to use Elastic Beanstalk. Now, Beanstalk supports a single container deployment directly on an EC2 instance and multi-container deployments on ECS. The benefit of using Beanstalk is that it can manage other resources aside from ECS, like your database and your Elastic Load Balancer. It also provides monitoring and logging for your app, and it's easy to set up multiple environments for one application. For example, you can have one environment for testing, another for staging, and one for production. This allows you to quickly create an integration stack that's identical to your production stack. Elastic Beanstalk's ideal if you want to leverage the benefits of containers, but want or like the simplicity of deploying applications simply by uploading a container image. You can work with ECS directly if you want more fine-grained control for custom application architectures. Now, if you're already using Docker Compose, you'll be glad to hear that the ECS CLI will allow you to run your application both locally and on an ECS cluster using the same Docker Compose YAML file. With the ECS CLI, you'll be able to run the same Docker Compose commands in your local environment and up, start, stop, and PS on ECS. The ECS CLI is available today, plus it's open source. So we encourage you to get involved by submitting your own enhancements. Now, here's an example of how you configure the ECS CLI on your client machine. You can either use AWS environment variables for your AWS access and secret key, or you can specify an AWS profile on your client machine. In this example, we're creating a new cluster called ECS CLI Demo in the US West 2 region. And here's an example of how you deploy an app as a task or service and how you'd scale that service once it was running. We purposefully mimic the Docker Compose syntax so it'd be easier for folks who are already familiar with Docker to use. So now that we've looked at the different stages in a continuous delivery pipeline, we're ready to automate it by orchestrating the tasks that are part of each stage. There are a variety of ways to do this, including building your own solution or buying an off-the-shelf solution from an AWS partner. The next few slides illustrate a few ways you can automate your pipelines. So in this example, Jenkins is used to orchestrate the different tasks in the workflow. In the first step, your code and your Docker files are pushed to a code repository like CodeCommit or GitHub. Jenkins then builds an image from those files and runs a set of tests against those images. Assuming the test passed, the image is then pushed to a private Docker registry like ECR or public registry like Docker Hub. During the last stage, Jenkins calls the ECS API to update your service with the latest image. This triggers a pull from the registry, and new instances of the container are deployed onto ECS. We'll have a look at a slight variation of this when we get to the demo. Now, Jenkins is a popular choice for automating pipelines because it has a broad ecosystem of plugins and it supports webhooks and AWS Lambda. This makes it relatively easy to integrate Jenkins with the rest of the components in your continuous delivery pipeline. For example, there's a build and publish plugin that can build your Docker images for you. There's also a plugin for pushing your image to a Docker registry. Once you've got your pipeline automated, You can merge your code updates into the master branch and let Jenkins handle the rest. Here's a variation of the previous example. Only here we're using CodePipeline and a set of custom actions backed by AWS Lambda functions instead of Jenkins. For those of you who are unfamiliar with CodePipeline, CodePipeline is a continuous delivery service for fast and reliable application updates. CodePipeline builds, tests, and deploys your code every time there's a code change based on the release processes that you define. This enables you to rapidly and reliably deliver features and updates. You can easily build out an end-to-end solution by using a set of pre-built plugins for popular third-party services like GitHub, or integrate your own custom plugins into any stage of the release process as shown here in this pipeline diagram. Now, when new code is merged into the master branch of our GitHub repository, CodePipeline calls our first Lambda function, which is used to create the EC2 instance upon which the Docker image is built. After the image is pushed to the EC2 container registry, or ECR, another Lambda function, listening for a push event, terminates our build instance so we no longer incur costs for running it. Another Lambda function is responsible for updating the task definition for our service after the image is pushed to the repository. In the last step, a Lambda function updates the service with the new task definition, and a new version of the container is deployed onto the ECS cluster. Now, if you'd rather not build your own solution, some of our partners have created integrated continuous delivery solutions with Amazon ECS. We've already looked at Jenkins. Now we'll have a quick look at a similar solution from Shippable. So Shippable is a hosted cloud platform that provides hosted continuous integration, deployment, and testing to GitHub and Bitbucket repositories. You can create and run Amazon ECS services and tasks on your ECS clusters from within the Shippable Formations module. You can also pull and push Docker images from Amazon ECR as part of your Shippable CI builds and deploy them with Shippable Formations across multiple clusters in Amazon ECS without ever having to manually update a task definition yourself. Shippable will automatically update your ECS task definitions with the latest image information based on your CI builds and automatically deploy to production or deploy to production with a single click when you're ready. With that, I'm going to give you a brief demonstration of how you can automate a continuous delivery pipeline. Let me share my screen. Okay. So in this demonstration, I'm going to be pushing code to a GitHub repository. That's going to trigger a build using GitHub's support of webhooks. The build is going to occur on the Jenkins server, and using the build and deploy plugin for Jenkins, it's going to push that image into Amazon ECR. As part of our continuous delivery pipeline, Jenkins is also going to update the task definition for the service that's running within our cluster. And then finally, the service is going to be updated with that new task definition, and a new version of that container is going to be deployed across the cluster. Now, what we're looking at here is a Python Flask application. It's a simple application that accepts user input and stores that input in a DynamoDB table. And it looks as if a colleague of mine has vandalized this website. It says the next big thing is not coming. I want to change that to read the next big thing is coming. So I'm going to update that file within GitHub, contained here within the index file. And I'm simply going to, oops, look at it. Simply going to remove that word from the file. Then I'll commit my changes. And if all goes well, that's going to trigger a build. And I can monitor that. Let's see, did I? Let's see if I got to click it. Okay. Well, the good thing about this is that we can trigger a build manually. Oh, no, there it goes. Okay, so it took a little longer than I expected, but the build did occur and it was successful. Now let's have a look at how that job is configured. Come here, and we'll step through the different pipeline stages here. First thing I did was I granted Jenkins permission to my GitHub repository. I have a set of credentials that I'm using to access that, and these are the branches that I want it to build from. And I've also checked this box under build triggers so that when updates are incorporated into the master branch, it's going to use GitHub support of webhooks to trigger a build. Then I'm using the CloudBees Docker build and publish plugin to generate a Docker image. I'm using the build number as the tag, and I'm specifying that I want this image to be stored in the EC2 container registry. And then here, under the execute shell section, I am using that build number to update the task definition that the service uses. And then I update the service with the new task definition and the desired count. If the desired count is 0, then increment it to 1. And then finally, I use the ECS API, or CLI rather, to update the service. And I also am using the Slack plugin for Jenkins to have build messages sent directly to Slack. So you can see in this channel that I have several updates from Jenkins. These are the latest that correspond to build 41. Now if I come over here and I refresh the page, we should see that build 41 is now stored in the registry. And I come over here and I refresh the page, we'll see that ECS, or rather the application load balancer that is in front of the service running on ECS, is draining the connections to the old task that was running within the cluster and redirecting requests to the new task that's part of that service. Now, it's important to pay attention to these deployment options here. You can see that there's a minimum healthy percent of 50. This guarantees that 50% of the fleet will continue operating as the deployment is occurring. Until the deployment is sufficiently completed, then those tasks will be deprovisioned. Maximum percent is similar, only it's specifying the maximum number of tasks that can run within the cluster. And then if we come over here, we can monitor the application load balancer. You can see that it's currently draining connections to that specific instance, and it's redirecting requests to the new task. And if I come back over here to my original page, it now says the next big thing is coming. Now, I'm also using Griffin, which is a way for you to visualize the tasks that are running within your cluster. You can actually see that I've got two versions of the task running. I've got the old version, version 41, and the new version. The connections are currently being drained from 41 and being directed to 42. And I also have a task definition for Griffin. So if you haven't used this before, it's a handy way to see not only the different task definitions that are defined for your various services, but also where they're running within the cluster. So with that, that concludes my demo. Jerry, if you can revert back to the slides for me. Great. So I want to thank you all very much for joining us. Hopefully you enjoyed this session, and you'll now go home and start enhancing your continuous delivery pipelines by adding support for containers and ECS. If you have any questions, please enter them in the chat window now. We'll do our best to answer them in the time remaining. And before leaving, I want to remind you to take 5 minutes or so to complete the survey questions that Jerry talked about at the beginning.
Jeremy, I want to thank you for the great presentation, and I want to thank Drew and Daniele for the great support in our Q&A as moderators today. Please provide us your feedback on the polls on the left side of the screen. I see a lot of folks are already doing that. We do appreciate your feedback. We do have some time left to answer some Q&A questions, so feel free to enter those at the top middle of your screen right above our thank you slide, and we'll go ahead and respond to those verbally and through the Q&A panel. So again, thanks to everybody for attending today. If you have no further questions, feel free to disconnect, but we are running our Q&A session at this point.
Okay, great. So I see a question in here from Thomas McCracken about where can I learn more about Griffin. So Griffin is an open source project. I don't know what the URL is offhand, but if you search GitHub for Griffin, you should be able to find additional documentation about how to install it onto ECS. And there's another question in the queue about how blue-green is handled within service updates. So you would do that by using the min and max values that we looked at before during the demonstration. That will ensure that you have different versions of your service running within the cluster so that you can gradually drain connections to the old version of your service and redirect those to the new service. Now, if you want to have them run in parallel, you potentially run those in or across multiple clusters, or you can have you could use the path-based routing potentially to do that. Yeah, I'd have to think about that a little further about how you do blue-green. Good question, though. So I see another question in the queue here from Ian McAlpine. It says, what are the benefits of running CodePipeline alongside or integrated with another CI tool like Jenkins? So, I'd say that there's a lot of overlap between CodePipeline and Jenkins. I'd say that the benefit of using CodePipeline is its integration with the rest of the AWS ecosystem. CodePipeline has a pretty good support for a lot of popular continuous delivery tools, as does Jenkins. I'd say it's really your preference. If the integration with the rest of the AWS ecosystem is important to you, then I would consider using CodePipeline. Otherwise, Jenkins is a fine choice. So there's a question in the queue here from Baruch. It says, how do I build the promotional pipeline in my registry? How can I separate the dev repository from production repository and promote from one to another? How can I make sure that I always deploy from dev repository to dev server and from prod 1 to prod? So if I understand your question, you want to know how you can promote images from one container registry to the next and deploy those into the appropriate environments. So you can have multiple container registries. You can have a registry for staging and another for production, and you can configure your pipeline such that it stores those images in the requisite registry. There may be things that you can do beyond that within Jenkins and CodePipeline, but I'd have to look into that.
I'd like to spend a special thanks for our presenter today to Jeremy for his time and a great presentation on the content today. I want to also thank Drew and Daniele for answering all the audio questions in our Q&A panel, so thank you for that today. If you have any comments on the previous and upcoming webinars or any suggestions on the topics that you wish AWS to cover in the future webinars, please feel free to email us at aws-webcasts@amazon.com. Your feedback will help us improve our webinar programming. Again, thanks to everybody for joining in today,